For the first talk, we have David Schmid from the Perimeter Institute and I guess also University of Waterloo, who will be telling us about the interplay of entanglement and non-locality and the new branch of entanglement theory. So David, please go ahead.
Thanks so much for the introduction. I'll go a bit slow since we started a minute or two early, in case anyone's still showing up. So as Velocity mentioned, I'm going to be telling you about this new branch of entanglement theory and how we use it to understand the interplay between entanglement and non-locality. This is work done with my collaborators, TC, Ravi, Belen, Ellie, and Rob, and also some other collaborators were involved on some related papers that kind of tied in here. And if you're interested, you should check out the paper here on the archive. In fact, if you already looked at the archive paper more than a week or two ago, you should take a second look. We've uploaded a revised version, which has a couple new sections, and the self-testing section has been significantly revised. All right, so what is entanglement? Well, entangled states are those that are not a mixture of product states. That is, they're the non-separable states. They're also physical resources in the sense that they can be consumed to carry out useful tasks. And they were first studied as a resource for non-classical communication tasks, like teleportation and quantum Shannon theory. So in this context, classical communication was considered free. That way, the thing you're trying to achieve, the non-free stuff, is the non-classical communication. And local operations were also considered free because they don't induce any correlations between two distant parties. So over time, entanglement came to be understood as the resource which cannot be generated by LOCC operations. And this leads to an entire resource theory of entanglement, which is based on a single simple idea. A state rho 1 is at least as entangled as a second state rho 2, if and only if you can convert rho 1 into rho 2 using these free operations, the LOCC operations. And based on just that one idea, you can derive the whole structure of the resource theory. And in particular, you can derive measures of entanglement, that is LOCC monotones. And these are used in a wide array of physics. So they're used when studying entanglement entropy of ground states, when studying the black hole information paradox. They're really used in this dramatically broad scope of physics. And this leads to a kind of puzzle. Why would a theory developed specifically for understanding quantum advantages in communication tasks be the most relevant way of quantifying correlations in these much broader contexts? And our answer is going to be, it isn't the most relevant way of doing this. So let's start by noting that there's a second possibility for defining a resource theory of entanglement. If instead of allowing classical communication, we allow some weaker resource of shared randomness, so some classical random variable that's sampled, prepared according to some distribution shared between two parties, then we end up with a resource theory, which has the free operations being local operations and shared randomness. This is the LOSR resource theory. And what you find is that this definition reproduces the separable entangled divide in exactly the same way that the LOCC resource theory does. However, it's a quantitatively very different notion of entanglement. So the conversions that are possible with shared randomness rather than classical communication are very different. And in particular, while this LOSR resource theory reproduces all the LOCC monotones, it also leads you to a whole bunch of new monotones. So this kind of explains why, in contexts where LOSR is the more relevant notion, LOCC monotones are still useful, they're still valid monotones. It's just you're going to miss out on some insights if you only use the LOCC monotones. Sometimes there'll be LOSR monotones that give you more information than you can get from the LOCC monotones. But okay, so we have two possibilities now. This just raises the question, in some given context, are the relevant free operations for studying entanglement LOCC or LOSR? And the answer is, it depends. The appropriate notion of entanglement depends on the network structure. So just to give a little plausibility argument, we give more detailed arguments in our paper. If you look at these tasks like teleportation and quantum Shannon theory, you can see that to achieve teleportation, for instance, we need this classical communication. In contrast, for LOSR entanglement, this is going to be relevant in scenarios like Bell scenarios and the study of non-locality and the kind of tasks which are built around them, like key distribution and randomness generation. In these tasks, you have a different network structure. It's a common cause network structure. There's no communication between the parties. In fact, it's forbidden, or it's not allowed by relativity. So to put it another way, if you're trying to study entanglement as a resource for non-classical communication processes, then you should allow the classical communication for free. If you're trying to study entanglement as a resource for non-classical common cause processes, then you should allow the classical common causes for free. So you always allow the classical stuff for free so that the valuable resources are the non-classical versions of the kind of process that you want to study. And instead of kind of harping on this point, I'm going to just assume that you're on board with this idea, and I'm going to tell you what follows. So what do we learn if we start studying this LOSR notion of entanglement? And the first thing we learn is that you can have a unified resource theory of entanglement and non-locality, which is something that people have kind of said vaguely in the literature wasn't possible, but it's absolutely possible. You just have to change your notion of entanglement to LOSR rather than LOCC. So entanglement theory is all about which states can be converted to which other states via free operations. And I've said the free operations in the context of a Bell scenario should be LOSR operations. So here we see a local operation on half of an entangled state, another local operation on half of an entangled state, and we're correlating our choice of local operations using our shared randomness. The study of non-locality is all about box-to-box conversions. That is, we consider the resource of interest to be the correlations themselves in the Bell scenario. So here's the box. It's a conditional probability distribution over these classical outcomes given these classical inputs. And then in green is the most general LOSR operation for converting a box to a box. So we've got some kind of local pre and post processings of the inputs and outputs, and then we correlate those processings with our shared randomness. And we kind of motivate why this should be LOSR independently in this paper here. And if you want to study the interplay between entanglement and non-locality, it's again LOSR operations. So here's an entangled state being converted into a box using LOSR operations. Now, normally when people study the interplay between entanglement and non-locality, they use local measurements. And we're proposing a slightly more general set of operations here, LOSR operations. So we allow for a correlated choice of local measurements. So in all three cases, you can and should, in the case of a Bell scenario, study these concepts with the LOSR operations. And when you do this, it leads you to a bunch of new foundational insights and new technical open questions.
There's a question from Cyril. He's, okay, it's been answered in the chat. So single lines equal to classical and double lines equal to quantum?
Yeah, good question. That's exactly right. Double lines are quantum, single lines classical. So once you take this approach, you get a bunch of new foundational insights and new technical questions. So here's the foundational insights that we discuss in our paper. We resolve the anomalies of non-locality. We clarify and extend the notion of self-testing. We illuminate how one should understand Varner states and hidden non-locality. This is one of the new things we've added to the paper. And we come up with a better notion of genuine multipartite entanglement and non-locality. So I'm going to go through a couple of these in this talk. First of all, resolving the anomalies of non-locality. The anomaly is that sometimes people have found having more entanglement means you can't generate as much non-locality. There's been a ton of work on this. Here's a small sampling. So quantitatively, there exist measures of non-locality which can be maximized by a partially entangled state, but they can't be maximized by a maximally entangled state. It's kind of counterintuitive if you think that entanglement is the resource for generating non-locality. So for instances of this anomaly, consider the family of entangled states given by cosine theta 0, 0 plus sine theta 1, 1. As theta ranges from 0 to pi over 4, we go from the product state, which has no entanglement, to the maximally entangled state shown here. And it's well known that as theta increases, you have strictly and monotonically increasing LOCC entanglement. And you think surely having strictly more entanglement can't hurt you if your goal is to generate non-local correlations. But in fact, if you actually try using these states to generate non-locality, as measured by the violation of a tilted Bell inequality, relative entropy distance from the local set, extractable secret key rate, probability of running a Hardy proof of non-locality, any of these measures of non-locality, it turns out the optimal state is not the maximally entangled state, it's some state in between these two extremes. And furthermore, the optimum is different in each case. So it seems like there's just no connection between how much non-locality you can generate according to any of these measures and the amount of LOCC entanglement. They just seem to be completely independent quantities. This is what people have recognized in the literature, and this is what they called the anomaly because it seems counterintuitive. But now let's reconsider the same family of states with respect to LOSR operations. It turns out what we show in our paper is all these states are LOSR incomparable, which means no one of them can be converted into any of the others. Of course, with the exception of the product state here, which is completely free. So any state can be converted to it for free. So there's no single measure of LOSR entanglement in this context. Namely, there's one measure, which is just the LOCC measure, that's still a valid monotone. But there's another measure which has exactly the opposite behavior. So as you go from this product state up to the maximally entangled state, you get less and less entanglement. The least entangled state, other than again the product state, is the maximally entangled state, according to this monotone. And furthermore, for each anomaly, there's some LOSR monotone, which is peaked exactly at that optimal state for that task. So there's no more anomaly. We see that having more LOSR entanglement never means less ability to generate non-locality. It's just that according to one monotone, this state might have more non-locality according to this, this state has more LOSR entanglement according to this monotone, and it has more LOSR entanglement, and this second state has more LOSR entanglement according to the second monotone. And so they're each good for different tasks because they're each more entangled according to one LOSR monotone. So to summarize all this, the standard conclusion from the anomalies is that non-locality and entanglement are different kinds of resources. And our conclusion is, well, non-locality and LOCC entanglement are different kinds of resources. But there was no reason to expect these two to be related anyway, because LOCC entanglement isn't particularly natural in a Bell scenario. In contrast, non-locality and LOSR entanglement are manifestations of the same kind of resource, namely non-classical common cause resourcefulness. And indeed, once you recognize this fact, the anomaly of non-locality just goes away. You find that more LOSR entanglement means more ability to generate non-locality. Okay, so moving on to clarifying and extending the notion of self-testing. So the motivation behind self-testing is to learn something about the internal components of a physical process or some quantum device without opening it up and testing its individual components. And there's kind of a canonical example people give of this. If you achieve the quantumly maximal violation of the CHSH inequality at space-like separation, then the state that you must have been using must have been the LOCC maximally entangled state. Now, of course, there's a family of unitarily equivalent maximally entangled states. So there's never a unique state that can generate a given box. And furthermore, if you had two maximally entangled states, well, that could do the trick as well. Or 5 maximally entangled states, all of which are different up to local unitaries. So there must be some kind of freedom up to which you define self-testing. And people have traditionally taken that freedom to be some kind of local isometry freedom. So to say that a state psi is self-tested by a box or a correlation B is to say that that box can be obtained by local measurements on some state phi, only if the state phi can be mapped to psi with some garbage state by a local isometry. So if you're not familiar with this, it might sound a bit complicated, but the idea is quite simple. The goal is to infer that whatever state was used to generate your observed correlations, that state can have the state rho extracted from it. You can convert the state that was actually used into rho. That's what it means to self-test rho by a box B. And I want to just note a couple of points about this definition. It's only defined for pure states. And in fact, people often claim that mixed states cannot be self-tested. And there's no real justification for choosing local isometries. It leads to an interesting question, which leads to interesting results. But it's really just kind of a made-up condition as far as I'm aware. So we like this basic idea. We want to study this kind of notion of self-testing. But we want to see what it looks like within our LOSR framework. And we've already argued that the appropriate set of operations for talking about converting a state into another, that's like extracting rho from whatever state was used in your device, that's the purview of state-to-state conversions. And we've argued that you should use LOSR to study state-to-state conversions. Similarly, converting the state in your box to generate some correlations, we've said that should also be studied using LOSR. That's a state-to-box conversion. So we're going to be led to a different definition of self-testing. we say that a density operator rho is self-tested by a box B if it holds that rho can generate B, and any other state sigma that can generate B can also generate rho, where everything is, of course, evaluated relative to LOSR. So to put it very, very simply, every state that can generate your observed correlations has to have at least as much LOSR entanglement as the state that you're self-testing. That's all it means. To self-test a state rho means to say, my correlations indicate to me that whatever state was used better have at least as much entanglement as the state that I'm self-testing. So some consequences of this definition. Well, first of all, we show in our paper that some mixed states can be self-tested. And furthermore, there's some non-extremal quantum correlations that can self-test various quantum states. And also, we have now a principled approach to self-testing. So we have a justification for the choice of freedom that we put in our definition. And we show that sometimes, under some special conditions, this reproduces the local isometry definition choice of freedom that's used in the standard definition. But in general, it's a different definition, and it's one that is better motivated than the kind of ad hoc choice of local isometries. And furthermore, by taking this principled approach, it also leads naturally, it kind of tells you more clearly how you should generalize in new contexts. So for example, it suggests a weaker notion of self-testing that always succeeds. No matter what correlations you observe, you can do some kind of self-testing. It's just that you'll get more or less information depending on what correlations you've observed. So we talk about this a little in our paper. And we also talk about how you can use this principled approach to generalize more naturally to other resource theories. So you can define self-testing even outside the context of entanglement and non-locality in other kinds of resource theories. And furthermore, you can talk about things like self-testing of steering assemblages, self-testing of quantum channels, and any other type of LOSR resource, where what I mean by that is we look at black boxes which have inputs and outputs, where those types can be trivial systems, classical systems, or quantum systems. And as you vary over the different types of systems, you get a whole bunch of kinds of resources that have been studied in the literature, and they can all be unified within our LOSR resource theory. And we do that in some depth in this paper here. And you can define self-testing of all these guys. Okay, moving on to Varner states. So what do we learn about Varner states in our framework? Well, so what are Varner states? The fact is that some entangled states cannot violate any Bell inequality. This is what Varner recognized. So to put it graphically, there exist some states rho such that every box you can generate from them by these local measurements or even by LOSR operations is free. So it doesn't violate any Bell inequality. And yet some of these same states can violate Bell inequalities if you first apply some kind of filtering or sequence of measurements. So in other words, if you take this state and you apply some measurement and you post-select on a particular outcome, then you can violate some Bell inequality. So people have referred to states of this first type as local states, and the ones that can furthermore have the second property are said to be local states with hidden non-locality, because to reveal that non-locality, you have to first do something like this filtering. I'm not going to use any of this terminology because, first of all, terms like local are just super overloaded, so it's not a great term. But more importantly, I'm going to argue this isn't really a well-posed property of a quantum state, or it's not the fundamentally interesting question about a quantum state. So let me explain what I mean. First of all, note that you can kind of see that there's going to be something generic to this kind of phenomenology in any resource theory that has multiple types of resources. In particular, it's not surprising that you can find some type of resource which can be converted to some other type of resource in such a way that you're forced to lose your resourcefulness. It's also not, and the reason for this is because the second type T prime, there'll always be some really trivial types of resources in your resource theory, say something with no inputs and no outputs. Of course, if you convert to such a trivial kind of object, it will destroy all the resourcefulness of your initially resourceful state. Alternatively, if you change from one type T to another type T double prime with free operations, and the second type is kind of more powerful than the first type, then of course you'll be able to do this while preserving resourcefulness. It just kind of depends on the relative complexity of the two types of resources. And to put it a bit differently, the general question here is, when can you take one type of resource and encode the non-classicality of that kind of resource into the non-classicality of another type? So Varner was asking, when can I encode quantum state type non-classicality into box type non-classicality? And he found that you can't always do it. And that's certainly an interesting question, but it's just a small piece of a much bigger puzzle. And we start to study that bigger puzzle in this paper here. In particular, we look at all these different types of resources. Varner was just asking about these two, and only in one direction, from quantum states to boxes. But you can ask about any one of these in relation to any of the others, and you can ask, when can non-classical steering assemblages be converted into non-classical distributed ensemble preparations, for example? And so there's a whole hierarchy here of different kinds of types of resources and which ones can be converted into which others. Varner states are just one little example here. And we proved some other results in this paper, and there's still some open questions. So that's the kind of bigger picture question. The main point, tying it back to this idea that states have some kind of locality or hidden non-locality, is questions of preserving non-classicality when changing from one resource type to another are completely independent of the question of how you define or quantify resourcefulness of a given type of resource. So for example, the definition of entanglement is completely independent of what kinds of possibilities you have for converting entanglement into other kinds of resources. In particular, generating a non-local box is a sufficient condition for a state to be entangled, but there's no reason to expect it to be a necessary condition, and it's not a necessary condition. That's what Varner showed us. So to say it again, the divide between free resources and non-free resources, that is between entangled and separable, is defined by the physically motivated set of free operations. And this physically motivated set of free operations tells you what the free operations are for resources of all types, not just for one type, but if you have a kind of physical restriction, it will naturally tell you, as we saw earlier, like the LOSR operations could be applied to states, to boxes, or even type changing conversions. So the takeaway is hidden non-locality, unlike entanglement, is best viewed not as an intrinsic property of quantum states. Rather, it's a property of what kinds of conversions are possible from states to other processes. So it's not about the intrinsic properties of quantum states so much as it is about what you can do when you're converting quantum states into some other type of resource, in this case, box type resources. And really, to hopefully hammer this point home a bit more, typically, we've started historically by studying the Bell scenario. You have entanglement type resources and you're converting them into box type resources. That's what Bell considered and Varner considered. Then people realized if you allow the causal structure to change, that like in this filtering scenario, you have a different causal structure, you have more possibilities of witnessing the entanglement that's intrinsic to the quantum state. And if you go to even more general cases, like this causal structure considered by Bowles et al., you find that any entangled state can have its non-classicality witnessed in a process of this type. Alternatively, you can keep the same Bell causal structure and you can change the input-output types of this black box here. So that was what was done, for example, by Buscemi and by others. So Buscemi showed that if you change the input types of this black box to quantum systems rather than classical systems, then you can again witness any, whatever entanglement you have in your quantum state, you can always witness it by studying processes of this type. So now we see that there's kind of this whole zoo of possible ways of probing the non-classicality in your quantum state. In every case, that non-classicality is best defined by the LOSR operations and by LOSR entanglement measures. So we have a resource theory of LOSR entanglement to study just the state type resources. But if you want to understand the different possible ways of witnessing that entanglement, maybe with just classical inputs and outputs, or maybe with just the Bell causal structure, then you're studying the possibilities of converting that kind of non-classicality into some other kind of non-classicality. And in every case, we're kind of asking for resources of causal incompatibility in arbitrary quantum networks. Where by arbitrary, I mean you can change the causal structure and you can even change the input and output types in general. And you can imagine, of course, that you could change both the causal structure and the system types. So this gets really crazy. And really the more general question is the one that I just described here. Okay, so if you're interested in all this, in our paper, we proved some basic results about the LOSR entanglement theory, which hopefully by now I've motivated to you why it's worth studying. So we proved, for example, an analog of Nielsen's theorem that is necessary and sufficient conditions for LOSR conversions between two bipartite pure states. But this is a pretty limited scope, so we'd like to have more general results about conversions. And we proved some other results as well, which I won't bother reading out for you here. I just want to close by noting that essentially, when people think of entanglement theory, they typically think of it as this kind of monolithic LOCC resource theory, which has a whole bunch of well-known results and applications. And we're arguing, really, this is just one slice of entanglement theory. It's the slice relevant to studying certain tasks, like non-classical communication tasks. In other scenarios, like the Bell scenario, there's an entirely new resource theory that's needed, an entirely new branch of entanglement theory, the LOSR resource theory. And we've started to study this. In fact, this resource theory was actually proposed by Buscemi many years ago. And it's just that no one has followed up on that work. They've kind of used ironically, they've used this paper for a number of important practical applications, but nobody has actually studied the resource theory that he proposed within it until we have done so in our paper here. And furthermore, in still other networks, there's going to be still other resource theories. You don't always apply the LOSR resource theory either. You got to look at the network and you figure out what the appropriate way of quantifying your correlations is. And so people have also started to recognize this fact, for example, for genuine multipartite entanglement and genuine multipartite non-locality. It's relevant to think about the network structure, and it leads you to the definitions proposed in these works here, one of which is the paper I've been talking about. And there have been more recent works as well. So that's all that I have time to tell you about. These are the most relevant papers. Thanks for being here, and I'll take any questions.